And the reason why we are studying actually magnetic circuits in this course, because it is used in the power grid as we see in this slide. Where it is used in transformers, for example. And we know the importance of transformers in this power grid, because we need to use it to step up, to step down the voltage. We step up the voltage because we need the transmission lines to be high voltage so that we minimize the current, and as a result the losses will be also, power losses will be minimized. And we need also to step down because the voltage utilization level is relatively low. So from the transmission to distribution, to distribute the power and connect the power to the customers, we need to step down the voltage. So transformers, they are used as a step up or step down transformers. And the concept of transformer is based on magnetic circuits. So that's why we are studying magnetic circuits. Also, we use magnetic circuits in machines. And again, machines are important components of the power grid, either as generators or as motors. So generators, they are used in the generation system. Motors, they are used in the distribution side. Again, so we need to know about the magnetic circuits. So we're going to study in the coming today and also the coming 3 classes magnetic circuits, some basics from physics, and also analysis of magnetic circuits. Before I start the lecture today, we're going to post the homework for both magnetic circuit and transformers this weekend. The next test will be covering magnetic circuits and transformers together. Okay. If you remember also that we have in the syllabus class participation points, 4 points. Starting from today, I'm going to start basically asking questions in the middle of the class. Verbal questions about the lecture, about whatever I am explaining today or in each class. So I will ask individually couple of students, 3 students each class, in the middle of the class, at the end of the class. If you answer the question or at least you participated in a satisfactory way, I'm gonna give you certain points. I will try to do it for each student 2 to 3 times. At the end of the semester, this will be translated to the class participation. Okay. Okay. Any question before we start?
Doctor, it is about answering the questions or just participate?
Well, both, to be honest with you. Yani, if you don't answer the question, it's not a participation.
Mm-hmm.
So, yani, if you at least try to explain, even if you say a few things wrong, that's fine. Yani. But if you say that I don't know, it's not a participation. Yani. This is the point. I need to make sure it's similar to what we do in the class, and I mean physical classes. Class participation, it means that the student is participating inside the class, answering questions, paying attention. Do this also in online classes. But if someone basically is just attending himself and opening the lectures without paying attention, of course we expect that he should not get any grade out of this.
طيب
And
دكتور بتسأل بالأسامي أنت ولا وشلون بتكون الطريقة؟
yeah, I will ask by name.
تمام.
Okay. Okay. So today, what we are gonna do today, the whole class will be about reviewing and discussing some basics from, I would say, physics. You covered all of these concepts that we're going to talk about today in physics. So, but we need them in analyzing electric circuits. So, for example, Just give me a second. Okay, so we'll start with the concept of angular velocity. Velocity, we know the velocity, which is basically the rate of change and displacement with respect to time. If this displacement is angular, we call it angular velocity. If it is not angular, horizontal, we are calling this only velocity. So it's the derivative of the angle, for example, theta here, over time. So we are taking the rate, and this rate is now it's called omega, which is angular velocity. And the unit for this will be radians, because we're talking about angles. So angles can be measured either in radians or degrees per second, which is time. So it does make sense to have the unit as radians per second, or we can express this as revolutions per second. Revolutions, it means that we are counting basically the number of rotations for this angular movement. Or the last one, N, which is revolutions per minute, RPM. So we are familiar in RPM, right?
Yes.
Yeah, which you can see it, for example, in our cars as an indication for the angular velocity. Okay. So revolutions per minute is mostly used in practice more than any other unit that you see here for the angular velocity. So for machines, especially motors, we use, as I mentioned, angular velocity. RPM as the unit for the angular velocity. We have also what we call the acceleration. Acceleration is another derivative for the speed or velocity. So we know that, for example, first of all, we have the displacement. If it is angular, so we have theta. If we take the derivative of theta over time, this is velocity. If we take another derivative for this velocity, will be acceleration. So acceleration is a rate of change in velocity over time. So it's the derivative of the angular speed or velocity over time. The unit is revolution per second square. So we know now the angular velocity. We know the angular acceleration. Important factor usually we use in machines is the torque. And if you remember also, I mentioned at the beginning of the semester that in electric circuit, the electrical power is related or linked to two main components, voltage and currents. And you know that. We already discussed this in power calculations. And mechanical side, the mechanical power is related to two also important factors: the angular speed and torque. So to explain the torque, which is basically defined as the product of the force applied to the distance between the axis of rotation and the point of force. Let's imagine that we have these cylindrical shapes you see in front of you. And these are cylindrical. So if we apply force at this point, so the difference.
There is no torque.
Yes, exactly. Why? Because the difference between this line, as you can see, the dashed line, and this point, which is the center of rotation, is 0. So despite basically the amount of force that you apply here, there will not be any rotation in this cylindrical shape, because this F multiplied by the difference, which is 0, will be 0. So no rotation. But if you apply the force here, and there is also a difference between the line of force and the center of rotation, yes, we would expect, of course, now this cylindrical shape to rotate. And now we have torque. So the result of this force multiplied by the distance is the torque. So more distance, we expect more torque. More force, we expect more torque. So it's a similar analogy, of course, in electric circuit, where more voltage, more electric power, or more voltage, more electric power also. Sorry, more current also will give you more electric power. Similarly for the door, I mean the door, if you apply the force, the center of rotation will be at the end of the door. If you apply force at that center of rotation, and the distance is 0, the door will not move. But usually you apply the force almost at the farthest point of the center, right? So usually, yes, it's easy to open the door because we apply the force with large distance from the center of rotation. And another concept also we need to know for the magnetic circuits is basically what's called the Ampere's right-hand rule. Again, we studied this in Physics 102. This is relating basically the direction of current to the magnetic field direction. And the concept here is easy. If we have a current in a wire, the direction of the magnetic field resulted out of this will be using the right-hand rule. So the thumb will indicate the direction of the current. The remaining fingers will indicate the direction of the magnetic field. Okay? Is it clear?
Yes.
Any question regarding this?
What is the difference between the two pictures, A and B?
Yeah, I'm gonna explain this. Just give me a second. So the difference here, basically, what we are doing in the right side is we are basically increasing the amount of magnetic field. How we can increase the amount of magnetic field? We know that if we increase the current, yes, the amount of magnetic field will increase. Why? Because the magnetic field is linked to the amount of current in the wire. So more current in the wire will give you more magnetic field. But there are also other ways to do this, which is increasing the magnetic field. One way is, as you can see in the figure B. Well, we can increase the number of turns, which is called the number of turns here. Sorry. So instead of using one wire, we use multiple, like what we call coil, which is wrapping a wire around an object. And I will come to this object in a few seconds.
To increase the magnetic field, doctor?
This will increase the magnetic field. Why? Because it's like increasing the current. You are not increasing the magnitude of the current inside the wire, but you are increasing the current, the amount of current relative to the space itself. So this, it's like, if you remember,
You can say the time that.
Yes, basically, we discussed this with the inductance, if you remember, right? It's an inductance here. It's an inductor, basically. If you wrap a wire, it's an inductor, which is called also a coil. So what you are doing, it's like you are storing the electric field. You are not storing electric field, but yes, It's like you are delaying the current relative to the time. So current now will go through small distance in a longer time. كأنك تعصر الكرنت خلينا نقول. Okay, so this will make actually the magnetic field generated more, and you can imagine it. If you have this like configuration of wires, every time you take the right hand rule, the magnetic field will be to the inside and in one direction. Okay, so if you start, for example, in the wire, you will see that if your thumb indicating the direction of current in a wire, now the magnetic field will be from right to the left. Am I right? If you go with the wire
Yes.
again and again, will be also from the same direction, right to the left. So it's like every time and every round and every rotation of this coil, the magnetic field resulted out of this is from right to the left. Remember that you are not consuming current here, but as the result of current in a wire is a magnetic field generated across the wire. So yes, now more magnetic field will be generated if we have what we call number of turns. So more number of turns will means that more magnetic field inside this coil. Okay. Another way also to increase the magnetic field is to use special material. What do you mean by special material? Well, it's like electric circuit. If you want to increase the amount of current, well, you need to use conductors. Conductors, they have the capability of carrying or conducting electrical current. Good conductors, it means that they have less resistivity. Less resistivity, it means less losses. Okay? So there are different types of conductors. It depends on the cost. It depends on the certain properties. It depends on the resistivity. For example, one of the best conductors can be used as what? What do you think?
Copper.
copper and silver.
Not copper, of course. Copper is a cheap one. Not a cheap, relatively cheap. Gold, for example. Gold is one of the best conductors can be used for electricity. But can we use gold in our transmission lines and our connections at homes? No, of course not.
Most.
Silver دكتور.
Silver is a good also, but again, you always have this relation between the cost and the properties or the conductivity of the material. So copper is used usually. Why? Because it's cheap relatively and with good conductivity. So similarly also for the magnetic circuit, we have some materials that they can conduct magnetic circuit and they have good conductivity for magnetic field. So they can be used. Why? Because they are better than the air. So if we don't use this material that you see here, if we don't use this, what will happen? Well, we generate magnetic field, but this magnetic field now will be generated inside in the air, inside these wires. Well, we can do better than this, which is having another material like this. For example, iron is one of the best materials also for magnetic circuits. So we can use this material such that the magnetic circuit that generated inside will be much better. So more magnetic field now will be contained in this material than the air. It is, but again, it is not contained. Meaning that if you generate magnetic field using this, well, air is not as good as iron, for example, but you still have magnetic field. And the magnetic field now will be everywhere almost, right? Because if you generate magnetic field, it will go to the air and you will lose the magnetic field. And this is not the objective here. The objective is that you utilize magnetic field. So when we come next lecture to the circuit of magnetic field, you want actually this magnetic field to be similar to electric circuit in a circuit, going from one point to another point. How to do this? Moving the magnetic field from one point to another point using materials. You get the point? So yes, two methods can be used to increase the magnetic field, which is having the wires in turns. So the number of turns will be related to the strength of the magnetic field. The current also is a factor of this strength of magnetic field. And also the material that we use is an important factor of this magnetic field. Good materials will increase the magnetic field. More number of turns will increase the magnetic field. More current will also increase the magnetic field. Magnetic flux, it's one of the main basically components of the magnetic circuit. It's similar to the voltage, current, and electric circuit. It's similar to the angular velocity and also torque and mechanical systems. Magnetic flux is a one important basically component or factor in magnetic circuit. The magnetic flux usually represented by lines moving from north to the south. So it's always this direction, from north to the south. And this is the component that representing the magnetic field. So usually when we say magnetic field in physics, we're talking about flux. Okay? We're talking about the magnetic field energy that moves from one point to another point. So these lines moving in this permanent magnet from north to the south, or these lines moving based on Ampere's right-hand rule and around the wire, or these lines moving also in the magnetic core, we call it magnetic core, inside the coil, all of them, they are the fluxes of the magnetic field. The unit of the flux is Weber. For example, in compass, usually the indicator is following these magnetic field flux lines. And the symbol is for the magnetic flux is phi, and the unit, as I mentioned, is Weber or WB. Another also factor or component is called the magnetic flux density. And from the name, density is density, meaning that it indicates, for example, how dense is the magnetic flux in certain area. So it has to do with the flux. It has also to do with the area. The symbol for the magnetic flux density is B, and it can be defined as the number of lines or magnetic flux per unit area. The unit is Weber per meter square, so makes sense, or Tesla, T. So the flux is related to the density by the integration, or you can see the opposite. The density is related to the flux by the derivative. And this is the equation here. The flux is equal to integration of density over area, or by area. If this density is constant, meaning that the distribution of a flux over area is constant, we can say directly that flux is equal density multiplied by area. Makes sense, because remember that the unit of this is Weber per meter square, and this is area, meter square. So of course, if you multiply both of them, they will give you Weber. Okay?
Doctor,
Mhm.
what exactly mean by the area? Is it the surrounding area or cross-sectional area?
Well, it depends. If we are talking, for example, about the area where you have a flux, if we are talking, for example, about this core or this material, if it is rectangular material, the area will be the cross-sectional area. It's like you are cutting this, and the area of this will be whatever you have inside this. So if it is square, if it is square. Okay? So we're talking about this area for this material where the flux is moving from one point to another point here. Okay.
Okay.
Another also factor, and don't worry about the different factors that we are discussing today. This is the main objective today. And I'm going to explain them more when we come, of course, to the magnetic circuits. Another factor, it's called the magnetomotive force, MMF. It's similar to the electromotive force, which is voltage in electric circuit. This is the ability of a coil to produce a flux. So remember when we said that if we have a coil, number of turns, and also have a current, the number of turns and current will give you magnetic field. That's true. This basically relation between the number of turns and current, it's called the MMF. Okay, which is the ability of the coil itself to produce flux. The symbol for this is F, and the MMF is equal N multiplied by I, where N is the number of turns of the coil, I is the current inside the coil. So this is similar to the voltage in the electric circuit. As a result, once we have this F, MMF, we can relate also the flux to this MMF. And the flux will be equal to F divided by R. So F is equal Ni. So it's like the flux is Ni or F divided by R. Again, flux is equal F divided by R. Where R here is not the resistive, the resistor of the circuit or resistivity of the circuit. It's called reluctance. And we are going to come to this. So now flux is equal F divided by reluctance. So to get a flux inside magnetic circuit or magnetic core, we need F. F will come from a coil, and it's a result of multiplying the number of turns of the coil by the current inside the coil. Then this F will be divided by reluctance, where reluctance is basically the property of the material or the core to conduct magnetic field, similar to the resistor and the circuit. So to get a flux, let's assume that my question is how we can increase the flux. What should you do based on this equation? Either
We
you
increase the number of turns
yes, you either you increase N
or increase the
Or
current
increase I.
or increase I
or reduce the
reluctance. Yes, that's correct. Once what's the meaning of decreasing the reluctance? Reluctance is a property of the material, right?
Yeah, changing the material.
Yes, either
Choosing
yes,
better
that's,
material.
What
that's
does it mean,
correct.
doctor?
We're gonna come to this in the next few slides.
Okay.
Reluctance is basically the property of the magnetic field. And there are certain factors that we are just going to discuss in the next slide. But yes, changing the material, of course, will make the flux either more or less.
Or can we install some obstacles inside the coils or?
You can manipulate, yes, because this R reluctance is not related only to the material, as related to the cross-sectional area, for example, to the length of the material. So there are a few things that we can do. By the end of this part, we will learn about them. So don't worry about this. So again, I want you actually now to link this equation, which is now, it should be very familiar equation to you, to the electric circuit. So this one is clear. It's similar to R in electric circuit, right? Similar to the resistance in electric circuit. F similar to what?
Power.
The voltage.
Voltage. Flux similar to what?
Current.
Current.
Ohm's law.
Ohm's law. That's exactly the same or similar to Ohm's law. So basically what we are seeing here is that flux is similar to the current in electric circuit. And it's true. Remember when we usually discuss the electric circuit, we usually use the analogy of water pipes, right? We say that the current is like the water in pipes. Voltage is like the pump in the water system. Wires, they are like the pipes in the water system. And here, resistance also is like the wheel in the water system, for example. Here we are going to use the same concept, but comparing the magnetic circuit to the electric circuit. So flux is like the current in the electric circuit, meaning that flux is moving inside the magnetic circuit from one point to another point, similar to the current. F is like the voltage in electric circuit, which is again similar concept, because F, it's like the engine or the source that makes actually the current or the magnetic flux move from one point to another point. So we provide the voltage to the electric circuit using a source. We provide also F to magnetic circuit using a coil through N and I. Reluctance is the same as the resistance in electric circuit.
So F is what is the unit of it?
MMF. It's called MMF, magnemotive force.
Is this related to Newton?
No. This is as I said, it's a notation used for the source of the magnetic field generated by a coil. So it's not a force, okay? It's a magnemotive force, yes, but it's not the absolute force that you learned in physics. So it's a magnetic force, let's see, just to be clear about this. So this is the analogy here. It can be compared to electromotive force, voltage in electric circuit. And yes, causes current to flow in electric circuit. MMF causes flux to flow in magnetic circuit. So this is a complete magnetic circuit. It's not electric circuit. This is a magnetic circuit. What do we have in this magnetic circuit? We have number of turns, and we have also current. So as a result, what do we have here? We have also, because of we have number of turns and also we have current. As a result, F will be also generated, right? Which is N multiplied by I. So F. Then what? Since we have F, now we will start to have magnetic flux inside this magnetic core. What's the relation between F and this flux?
R.
So yes, F divided Ni, or F divided by the reluctance of this core. How we can specify the direction of this flux? Using right-hand rule. Yes. So yes, that's why answering the question why we use the magnetic core, because you can see that this magnetic core, the material, will allow us to move the flux in a specific path. And this is what we need in a magnetic circuit. But if we don't have this magnetic core, what will happen? Yes, we will generate magnetic flux, but it's going to be everywhere. Okay?
كيف دكتور؟ It will be in everywhere.
Yes, because if you don't have this magnetic core, once you inject current here within, now the magnetic field will be basically
بيتشتت.
Yeah, يتشتت. Well, it is not as strong as the magnetic flux in this. Why?
لا لأنه مو في مسار معين يعني.
It's gonna be weaker. Why? Because again, it's F R for the air. is much larger than R for the material, for example. So that's why we use the material, so that we can shape it in a circuit for, path, and also to get more magnetic field.
So, Doctor, we can call it the medium that carrying the flux.
It is the medium, yes, it is the medium. Okay. So magnetic field, another also couple of factors. One of them is called magnetic field intensity. Intensity, it has to do more with the length itself, not the area. So it is the MMF per unit length. It's like, we know what is MMF or F. If we divide this F by the length of the magnetic core, this will give us like the average MMF per unit length, which is called here intensity. The symbol is H, and the unit is amp turns per meter. So if we divide, the H here will be the F divided by LC, where LC is the mean length or the average length of the flux path or the magnetic core. Of course, we can substitute for F by Ni here. Also, H is called the magnetizing force. Reluctance. I already explained a little bit about reluctance, but this is the symbol for reluctance, and the unit is amp turns per Weber. From where we got this unit? From, if you remember the equation, that is Ni over R. I don't know why it's like this. Ni over R. So R will be what?
Ni over the flux.
Exactly. So yes, the unit will be number of turns. Amp indicate for the current, T for the turns, Weber for the... This is just to explain from where we get the unit here. So it's the reluctance of the core. And the equation for this reluctance is LC divided by mu A, where mu A, LC, we know that LC is the average length for the magnetic core. Mu is called the permeability of the material, and I'm going to come to this. A is the cross-sectional area for the material. So the reluctance of the whole magnetic core has three components. The length of the core, so more length, it means more reluctance. Makes sense, right? Similar
Yes.
to the wires, electric wires. More wires, it means more resistance. It also has to do with cross-sectional area. Less cross-sectional area, it means what? Higher reluctance, right?
less area المفروض يكون
Less area.
Yes, high reluctance.
high
higher
reluctance.
كأنه الممانعة أكثر تصير في الأماكن الأصغر. Mu, which is called the permeability, this is a property of a material. So material X has mu different than material Y. Okay? So if you put them together, the cross-sectional area, the length, and the mu, you basically get what? The reluctance. So three factors affect the reluctance of the magnetic core. The length of the magnetic core, the area, the cross-sectional area, and also the permeability mu. For resistance, we have similar also equation. If you remember from physics, LC, A, and sigma. Sigma here is the resistivity of the material. Again, similar to mu, but for resistivity. Okay? This mu has also another equation, which is called mu naught multiplied by mu r. So mu has two components also. Mu naught, which is basically the permeability of the air, it's a constant. 4 pi multiplied by 10 to the power minus 7. Multiply by what we call relative permeability, mu r. So for any material, if it is air, mu r is equal to 1. So mu is equal to 4 pi multiplied by 10 to the power minus 7. If it is any other material, iron, for example, you get for this iron, for example, a number, 1000, which is mu r. So mu r for the iron is 1000. So the total permeability will be what? 1000 multiplied by 4 pi multiplied to 10 to the power minus 7. Okay? So it is a composite of the permeability of the air and relative permeability. And that is an indication. For example, if you have a material with 1000 mu r, it means that it can basically conduct magnetic flux 1000 times better than the air. This is the meaning of this. I need to speed up a little bit just to finish. I'm almost done. But just give an example here. The steels used in modern machines have a relative permeability in range of 2000 to 6000. This means that for a given amount of current, 2000 to 6000 times more flux is established in a piece of steel than in air. Okay, so this is why we use the material, because it can give us more magnetic field for the same area. Just as a summary, we're gonna go through all the equations that we learned or concepts that we learned today about the magnetic circuit. Magnetic flux, the symbol is phi, and the unit is Weber. The equations that you need also to memorize about this is that flux is equal BA, where B is the density, A is the area. Also, flux is equal F divided by reluctance, where F is the MMF and R is the reluctance. F is also the magnetomotive force, and the unit is amp turns, and it is equal to Ni. And again, from this equation, F is equal reluctance multiplied by flux. And F is equal to LC multiplied by H, where H is the intensity. And the unit for the intensity is amp turns per meter, and it is F divided by LC. Also, B is the density. The unit is Tesla or Weber per meter square, and it's equal flux divided by A. And also there is one equation that I didn't mention. Yes, sorry, it's an important one. It's called B is equal mu H. So we are relating density to intensity through permeability. And we're going to revisit this more later, inshallah. Reluctance, the unit is amp turns per Weber, and it's equal LC divided by mu A. Where mu is the permeability, it's H divided by M, and it's equal to mu naught multiplied by mu R, where mu naught is 4 pi multiplied by 10 to the power minus 7. I know that it's relatively large number of equations, but if you think about them, basically we are dealing with only few of them. This one, okay? Yeah, the remaining will be just another forms of these equations. So make sure that by next class, inshallah, at least you memorize all of these equations and be ready, because the next step will be basically analyzing or using all of these equations and analyzing magnetic circuits. Okay? So I'm going to ask a couple of questions here, as I explained at the beginning, about the material that we covered today. Al-Haji Nadir. الحاجي. اوكي. يوسف الطليحي.
Yes, دكتور.
Yusuf, just explain to me the torque in your own words.
It's the force multiplied by the displacement.
What's the displacement?
والله I don't know دكتور.
Okay, thank you, Yusuf. Good. Bakshi Ali.
Yes, doctor.
Ali,
Yes.
what is the Ampere's right-hand rule? Just explain it to me also.
The Ampere, what?
The
Can you
right-hand rule.
repeat?
What is the right-hand rule?
Yeah, it's the rule that we can know where is the direction of the current relative to the magnetic field.
Okay, good. العوهلي أسامة. العوهلي. تركي المشعور. تركي.
Yes, doctor.
Okay, Turkey.
Yes.
Why we are using the configuration of the coil, number of turns, and also the magnetic core inside this coil?
والله I don't know, doctor.
Okay, thank you, Turkey.
Welcome.
العيسى مصطفى.
Yes.
Okay, what's the meaning of relative permeability, العيسى? Mu R.
I don't know.
Okay, thank you, Mustafa. Okay, so we're done for today, and I will see you, inshallah, tomorrow. Okay, so we'll have office hour up to 2 p.m. So if you have any issue, any question, you can stay. Other than this, inshallah, tomorrow we'll see.
Okay.
دكتور بالنسبة للسؤال اللي سألناه قبل البارحة عن السؤال اللي في الميجر
ايوه
ممكن تشرح علينا؟